Hello. In this video, we're going to be talking about stoichiometry. That's a big fancy word about a topic that's very important to understanding chemistry. And stoichiometry is the relationship between relative quantities of substances taking part in a chemical reaction. It's a relationship between relative quantities of substances taking part in a chemical reaction. It's actually from a combination of a couple of Greek words that mean measure of elements. This coin was termed early in the 19th century. And so we're not just talking about elements here, we're really talking about substances, which can be compounds or elements. And so it starts off with a balanced chemical equation. You got to have a balanced chemical equation. And so let's take something like the formation of water from molecular hydrogen, molecular oxygen, and look at those coefficients. What those coefficients are telling us, one way of looking at it is that 2 molecules of hydrogen reacts with 1 molecule of oxygen to produce 2 molecules of water. That's on the very fundamental level, the smallest amounts that we can have reacting. Another way of saying this would be say that 2 parts of hydrogen reacts with 1 part of oxygen to produce 2 parts of water. The ratio is 2 to 1 to make 2. Now, what we're going to be dealing with, of course, are moles. So another way of looking at this reaction is 2 moles of hydrogen plus 1 mole of oxygen reacts to produce 2 moles of water. And so it's this mole to mole ratio that's going to be very important. Let's look at this reaction. I'm taking nitrogen plus hydrogen, reacting them to make ammonia. And to balance this equation, we need these coefficients. And so it's telling us that 1 mole of nitrogen reacts with 3 moles of hydrogen to make 2 moles of ammonia. And so in all of this, we're remembering the law of conservation of mass. That matter is neither created nor destroyed in a chemical reaction. If we go back to Dalton and his atomic theory, the atoms are neither created nor destroyed, and they're not changing identity in the course of reaction. They're just rearranging to make new molecules. And so when we do stoichiometry, what do we measure in the lab? We don't measure moles, we measure grams. And so we have so many grams of reactants coming together to make so many grams of products. So we're going from grams reactants to grams products. But we can't do that directly. What we have to do is go from grams reactant to moles reactant to moles product to grams product. So throughout all of these, we're going to be doing these steps. And to do so, we're going to need to come up with a stoichiometric ratio that we're going to plug in that relates reactants to products, or sometimes it might be reactants to reactants, depending on what the question is asking. we might also call this a bridge ratio. And so let's look at this problem. Let's take 25 grams of nitrogen. How many grams of ammonia can be produced? What we're trying to do is calculate the theoretical yield. The theoretical yield is the maximum amount of product that can be made, assuming that everything goes to completion. There are no side reactions that take place, or some impurities in a reaction, something like that. So we're going to take grams of nitrogen, convert that to moles nitrogen, convert that to moles ammonia, and finally convert that to grams of ammonia. So that's our battle plan, or roadmap, if you will. So 25 grams of nitrogen, molecular nitrogen, 1 mole of N2 is the same as 28.0 grams of N2. Where did I get that? Periodic table. And now I need to get the moles of ammonia. So I want moles of ammonia divided by moles of nitrogen. But I need to put in my stoichiometric ratio that says that 2 moles of ammonia is produced from 1 mole of nitrogen. So I need a 2 in my numerator. So 2 moles of ammonia to 1 mole of nitrogen. And now I can convert to grams of ammonia. And that 1 mole of ammonia is the same as 17.0 grams of ammonia. And so grams nitrogen divided by grams nitrogen cancels. Moles nitrogen divided by moles nitrogen cancels. Moles ammonia divided by moles ammonia cancels. And I'm left with grams of ammonia, which is my desired unit. And if I do that on my calculator, I'll see that I produce 30.35 grams of ammonia. I've got 3 sig figs. This is an exact quantity, the ratio, and I've got 3 sig figs. So it means I can only have 3 sig figs, so my correct answer is going to be 30.4 grams of ammonia. And that's my theoretical yield, the maximum amount of nitrogen that can be produced. If I'm starting out with that many grams of nitrogen, and assuming that I have enough hydrogen to have everything go to completion. Let's see how much hydrogen was also consumed in this reaction. How much H2 was consumed. And so we're going to do a similar process. We're going to go grams nitrogen to moles nitrogen to moles H2 to grams H2. And so 25.0 grams of nitrogen. 1 mole of nitrogen is the same as 28.0 grams of nitrogen. Now I'm going to use my stoichiometric ratio that says that 3 moles of H2 is consumed every time 1 mole of N2 is consumed. And then I need to go back to grams hydrogen. So 1 mole of H2 is the same as 2.02 grams of H2. So now I've got grams nitrogen divided by grams nitrogen, moles nitrogen divided by moles nitrogen, moles hydrogen divided by moles hydrogen, and that'll give me grams of hydrogen. And to put that in my calculator, I'll get 5.35 grams of hydrogen. 3 sig figs, exact ratio. 3 sig figs, I got 3 sig figs. is a check. I can go back to my law of conservation of matter that says that the number of grams I start out with has to equal the number of grams I wind up with. Grams reactants has to equal grams product if everything is reacting exactly. So I got 25 grams of nitrogen plus 5.35 grams of hydrogen. Those are my reactants. To add those together, I'll come up with 30.4 grams of reactants. Using my sig figs. And how much did I predict would be made from the ammonia? 30.4 grams. And so I must be doing something right. So that's a way you can go back and check yourself at the end of a problem, see if the amounts add up correctly. And so that's our first example of stoichiometry.